Okay, so we're going to look at something called alternating series now. We'll start off right off the bat with an alternating series test. Here's what it says. The alternating series converges, and given by this formula here, converges if all of the following are satisfied. First of all, the sequence of terms, the sequence of terms a sub n must be positive. The sequence, so these are all positive aside from positive, negative here. The sequence a sub n is decreasing for all n past a certain point. Okay, that means that no matter what, it's strictly decreasing, or I guess it's non-strict, but we can't have points going up like this after a certain point. We can't have this sort of thing happening. And the sequence approaches 0 as n goes to infinity. If those three things happen, then the series is convergent. So here's just a quick example of what we mean by an alternating series. The first term is positive, then negative, then positive, then negative. That's an alternating series. This negative 1 to the n power is a nice easy way to write that idea of positive, negative, positive, negative. Notice negative 1 to the 0th power is 1, negative 1 to the first power is negative 1, negative 1 squared is positive 1, negative 1. So this is the alternating part of the series. These are always positive. Okay, let's look at some examples here. So again, before I do that, these are what we're looking for when we're looking to see if we have an alternating series that converges. We must have positive terms, the positive terms must be decreasing, and the sequence must approach 0. If that's the case, then we automatically have a convergent series. So this is an alternating series. Okay, as n increases every step, this goes from positive to negative, starts at n equals 2 and goes on. So just quickly, just to see what this looks like, this is 1, and then the next one is negative 1/2, positive a third, negative a fourth, and so on. That's what we have. Now remember that the harmonic series is divergent. Okay, this is divergent. However, let's look at this. Okay, all the terms of this are positive. So we're looking at all the things here. The terms must be positive, check. The sequence must be strictly decreasing, and the sequence must approach 0. This sequence is strictly decreasing. It goes 1, a half, a third, a fourth, okay? And this is approaching 0, okay? So even though the harmonic series is not convergent, the alternating harmonic series is. This is convergent by the alternating series test. Let's take a look at this one. Okay, so we have an alternating series. That's step 1. Okay, these terms are always positive. Okay, this sequence better be decreasing. Okay, so we start off with 1. We have 1 over 1. Then we have 1 over 0. We can't put that in, so we start at actually has to start at 1. So we have 2 over 1. Then we have 3 over 2. Then we have 4 over 3. So this is decreasing, right? However, what's happening here is this going to 0. Okay, has to be decreasing, and this must approach 0. Well, we know that the limit of something like this goes to 1. So this does not converge by the does not converge, at least by this test. Okay, by the alternating series test. Okay, I haven't proved this divergent, but I have shown that it does not converge, at least by this test. Okay, let's take a look at this alternating series. We actually need to start it at 1. That's a typo. Okay, so this is an alternating series, negative, positive by this part right here. So we have to figure out a few things. We have to see, does ln n squared over n, first of all, this better be positive, it better go to 0, and it better be decreasing. Okay, that means basically we can't have this thing going up and down and up and down and up and down towards 0. This part here has to be going down towards 0. Okay, so let's check these things. First of all, I think it's pretty obvious that this will be positive because anything squared is positive, and n, by definition here, is positive. So the first part is fine. This sequence is positive. The next part we have to figure out is, does the limit as n go to infinity, of ln n squared over n, does that equal 0? Okay, well, this is infinity over infinity, so we can use L'Hopital's rule, if you remember that, which says that if I have infinity over infinity, I can take a derivative. So I'll use the chain rule to find the derivative of the numerator. So I find the derivative of the numerator and divide it by the derivative of the denominator. And now I have 2 times the limit, as n goes to infinity, of ln n over n. Again, I have infinity over infinity, so I can use L'Hopital's rule again. L'Hopital's rule, remember, you don't use the quotient rule. You take the derivative of the numerator divided by the derivative of the denominator. And this goes to 0. So good, that checks out. Sweet. It's positive, the limit goes to 0. Now we just have to show that it goes to 0 in a consistent manner. Okay? So we have to show basically that this thing is decreasing. It's a little tricky to do. It's not entirely obvious. It might be obvious, but we don't have a way to actually show that it is true. So we'll use our knowledge of derivatives. Let's take the derivative of this function. All right. So here we do need a quotient rule. Low d high minus high d low. Low d high, and remember I have to use the chain rule here to find the derivative of ln x squared, minus high d low, which is 1, all divided by low squared. Okay, the x here cancels with the x here, and I'm left with 2 ln x minus ln x squared over x squared. So on the top I have ln of x times 2 minus ln of x. It's over x squared. Okay, so now we have to evaluate if this derivative is negative, then the function is decreasing. Okay, if the derivative after a certain point is positive, it's increasing. Well, let's decide whether or not this, for large values of x, is increasing or decreasing. Is it positive or negative? This is positive. This is positive. So what we have to figure out is this positive or negative? Well, okay, 2 minus ln of x. This is an increasing function. ln x is getting big. Is it getting big fast? No, but it is getting big. So ln of x is increasing, and this is constant. So I have a constant minus an increasing function. This is always less than 0 after a certain point for x bigger than some number. That's all we care about. After a certain point, this becomes decreasing. So this is negative. These are positive. The derivative is negative, which means that after a certain value for x, this is a decreasing function. And since we have a limit going to 0, a decreasing function, and the function is positive, a decreasing sequence, and the sequence is always positive, the alternating series is convergent. So this is a slightly more complicated example, and this is not necessarily the kind of example that's going to show up on the AP exam all the time, but it's a good illustration to show you how in a more complicated situation the alternating series test might be useful. Okay, so another way we can use the alternating series is by using something called the alternating series error bound. So I've got an alternating series and I want to figure out how can I estimate the value of the series. Here's what it says. I've got my series, it's alternating. I have the -1 to the n times the series, and it's a convergent alternating series. So it's got to pass all the things we saw in the previous example. What this says is that the error, this is pretty neat, in using the kth partial sum to estimate s is less than the next term in the series, which is pretty cool. Okay, so if I want to use s sub 10 to estimate the sum, we can do that with an error bound, which is pretty cool. All right, let's take a look. So what I want to figure out s sub 10 first of all. And for that, we're going to use the calculator. Okay. Oh, that's not what I want. Okay. For that, I want to use the calculator to find the sum of the first 10 terms. So here we go. Okay, so I just went ahead and paused it and got the answer here. And I used the calculator to do this, to do it real quickly. So the sum of the first 10 terms is 0.9496. So at 0.94699. We'll just go out that far. To be clear, this is not a skill I need you to have in terms of being able to use the calculator to sum up 10 terms. Now, if you wanted to, and if I gave you a problem like this, you could actually do it in the calculator and add point by point by point up to the first 10 terms. But that's not a skill necessarily that I need you to have to be able to do this sort of thing. Okay, so don't worry about that. This is to illustrate how this theorem is used. So the first 10 terms is 0.94699, and we want to use the alternating series error bound in order to figure out how close are we to the real value. Well, this says that this is an alternating convergence series, right? This is 1 over n to the fourth, that's a p series, and it's made alternating. So the 10th term, sorry, the first 10 terms sum to this. The 10th term, so for n equals 10, if I ignore the alternating part, is going to be 1 over 10 to the fourth, which is 1 over 10,000. Okay? What does that mean? That's 0.000123301. So this is accurate. Pardon me, the entire sum is accurate to within that accuracy. Okay? So we know, in a certain sense, that the sum is 0.9469 something. Okay? Or I suppose it could be 946, okay, because that could have been rounded up. But in any case, we can only be off by 1/10,000th. That's what the alternating series test does for us. So it gives us an error bound, an easy way to find the error bound. Okay, last idea here is the concept of absolutely and conditionally convergent. You can read this yourself here. Basically, I'm going to summarize it. And what it says is that I have this notion of something called absolutely convergent. And that is if I have a series, a sub n, being summed up to infinity, if I take the absolute value of every term, we call that, and that thing converges, that is called absolutely convergent. If, however, I have something and this converges, pardon me, the absolute value does not converge, and yet the original does, we call that conditionally convergent. So a good example of something that is absolutely convergent, so pardon me, that is not absolutely convergent, but is only conditionally convergent, is that first series we saw. Let me go back to it. This one right here. We know that 1 over n, if I got rid of this part, 1 over n does not converge. However, the alternating series does. So the alternating series converges. If I take the absolute value of every term and add those up, it does not converge. So we would call this alternating series conditionally convergent. Okay. If we look at the one we just took a look at, this series right here, 1 over n to the fourth is convergent. It's a p series. The alternating series is also convergent. Okay. So what does that mean? This is absolutely convergent. So here's an interesting theorem that maybe you thought of already, and that says that if the absolute value of every single term added up converges, then automatically, if I remove the absolute values, that converges too. Okay? So absolutely convergent is more powerful than conditionally convergent. Let's look at a couple series here and get a sense of how these things are in practice. We're going to try to figure out if it converges, if it's absolutely convergent, or only conditionally convergent. So let's take a look at this first one right here. Okay. First of all, does it converge? This goes to 0, we know that. This is an alternating series. This goes to 0, and every term is going to get smaller. Okay. This is convergent by the alternating series test, so we know it's convergent. Let's decide if it's absolutely convergent or only conditionally convergent. Okay. So we know that it's conditionally convergent at least, because the original series converges. We want to find out, does the absolute value of this converge? Well, taking the absolute value, the only thing it changes is we don't have any negative terms out front. So this is equal to this series right here. Okay. And going from 2 to infinity. The question is this convergent? Well, we could use the comparison test, the direct comparison test, to compare this to 1 over root n. Or we could use the limit comparison test, really. And we know that this is divergent because it's a p series with n to the 1/2 power. So This is divergent because p is less than 1. This is divergent, which means that the original series is convergent, the absolute value of this series is divergent, so this is what we call conditionally convergent. Let's take a look at the second one. We have negative 1 to the n times 5 over n cubed. This is convergent. Okay, it's an alternating series right here. It's times every term here is positive, the limit goes to 0, and we know that every single subsequent term is getting smaller, right? This is always going to be less than, pardon me, is always going to be greater than the next term. So by the alternating series test, this converges. Okay, so we know it converges. That's good by the alternating series test. Let's find out if it's absolutely convergent. So if I take the absolute value of this, the only thing that changed now is that we never have a negative term. So that means this part right here is gone. And the question is this convergent? The answer is this is a p-series, 1 over n to the p, 1 over n to the third. This is a p-series where p is greater than 1, which means that this converges. So not only does the original series converge, but the absolute value of this series converges, which makes this absolutely convergent. Next one. This is going to be a little trickier. Okay, so we need to figure out where this goes. First of all, let's take a look and see if this converges at all. It's an alternating series. This must go to 0, and this terms must be getting smaller. Does this go to 0? Well, the limit, I don't know what that means there. The limit of n squared plus 1 divided by 2n squared plus 3, as n goes to infinity, is a half. So this doesn't even go to 0. The original series itself isn't even convergent. This is not convergent by the alternating series test. Okay, so we cannot prove that it's convergent, so it's not going to be absolutely convergent either. And finally, this last one, n equals 1 to infinity, sine of n over n to the fifth. Now notice this is not strictly an alternating series. It's not set up as negative, positive, negative, positive. Okay, some of the terms are negative and some are positive. So it's not exactly an alternating series. That's kind of weird. And this is going to be really hard to use any comparison tests on. However, we can say that the absolute value of this has some interesting factors. Okay, let's figure out what happens here. The numerator here is going positive, negative, positive, negative. So all the other tests we've had up to this point don't apply. Every single other test we've had has said that the terms, each individual term must be positive. Now let's take a look at this. Well, let's try to figure out if this converges. Well, can we compare this with anything else? We know now that the numerator oscillates between positive 1 and negative 1, and we're going over negative into the 5. So that series is bounded above by 1 over n to the fifth. This is a convergent p-series when I take the sum, which means that I have a convergent p-series that bounds another series, in this case an absolute value. Okay, so this is convergent, which means this is convergent. Okay, the absolute value of the series is convergent. So since the absolute value of the series is convergent, by the original, by this theorem, theorem 7.R, every absolutely convergent series is also convergent. So this, since the absolute value of this series is convergent, we call it absolutely convergent. Okay, and what that means is that the original series is convergent. This is convergent, and it's also absolutely convergent. Okay, so absolute convergence is stronger. If you can get absolute convergence, you automatically have convergence. So if you ever take the absolute value of a series, if you find it converges, that's enough to show the original series converges too. We call that absolutely convergent. Okay, series of convergence test, last little thing, in order. And we put the alternating series test right on top because it's really kind of nice and easy. Does it alternate? Does it go to 0? Is it positive? If those three things happen, it's convergent. So adding the positive negative up front make some series that were not convergent before now convergent. Okay? And that's it. I'll see you guys next time.